Hello students, lecture 27, ideal transformers. Again, hopefully within the 50 minutes. Now, we're going to start talking, what do we mean with ideal transformers? Just plug that in. Ideal means no losses. Everything works perfect. All right. Knowingly, that it doesn't exist. All right. It's like the ideal person. It doesn't exist. There are always character flaws that we need to work on. Just so with transformers, we're going to first look at ideal, meaning no losses, no core losses. In other words, no hysteresis losses. There are no eddy current losses. There are no I2R losses in the coils because you've got currents flowing through the coils. No losses. All the power that comes into my transformer just goes out on the other side. All right. Almost said something. But anyway. So why do we use transformers in AC circuits? So I've got a little diagram here on my board. This is typically your ESCOM power station. All right. And we're looking at around 6,500 volts. Now we need to get that power to your house. But there's a couple of problems because in between there needs to be transmission lines. As we send that current through to our side, it's extremely long conductors. I mean, you can think from Mpumalanga down to where the Cape is, it's almost 2,000, well, it is about 2,000 kilometers. And that length of line, the longer a line is, the higher its resistance. I squared R. Now you want to send all that power through the current to the other side through that resistor. There's nothing going to be left over when it gets to you on the other side. All right, it's like most politicians in the world. You give them some money and nothing comes out on the customer side. All right. So you're going to have losses. So how do we do that? You need to up the voltage. So in here, where's my chalk? You get a step up transformer. It steps up the voltage to higher. So from here down to the Cape, they step up the voltage to 765,000 volts. All right, 765 kilovolts. Three phases now. That's line to line voltage, three phase. But you typically don't want 765,000 volts in your house. You can just imagine if you shock yourself, well, there's not going to be much left in terms of insulation. So we need, on the customer side, we need to step it down again. And that happens in stages. It doesn't go from 765,000 down to the 400 volts that you have, line to line voltage. I know your house is 240 volts, 230 volts, but that's a line to neutral voltage. The line to line voltage in suburbs is 400 volts. All right, so we need to step it down again. Now, typically, the longer distance isn't 765 is an exception. Usually, it's around 400,000 volts. And when it gets into Tshwane, for instance, the substations are sitting at 132,000 volts. That goes down to 11 or 22,000 volts. And the substations, typically in your house, residential area, that's the word I'm looking for, residential areas, takes it from 11,000 to 400 volts. So next time you walk past or these green substation boxes that you see next to the road, most of them you'll see 11 kV to 400 kV. Not 400 kV, 400 volts. Okay, so by stepping up the voltage and the power remaining constant, well, if the power remains the same but the voltage goes up, what happens to the current? It goes down. All right. Well, remember S equals VI conjugate. So if V goes up, current comes down. What happens here to the I2R losses? If the current halves, your power loss is a quarter of what it initially was. So by stepping up the voltage, we are reducing those transmission losses. All right, I2R losses. And then on the customer side, we bring the voltage down again to safer levels. The current goes back up. And that effectively is the purpose for the transformer. All right, now let's go and look at what does a transformer consist of. So the symbol that I've got here, you'll see it looks like two inductors parallel with two stripes, lines in between. So those two lines just means that they're on the same core material. They're magnetically linked to each other. All right, so let's go and look what that looks like. So this is figure 1522 in your textbook. So we've got our source on the one side of the transformer, and terminals, current I1 coming in, V1 coming in. So footnotes 1 is denoted on the supply side. And then over on the load side, you've got I2 and V2. All right. It is connected through our transformer. You see the laminated iron core because it's going to be AC. So the current direction in reality is going to change the whole time because it's a cosine. I think up here, there they say that V1 is V1M. So amplitude, remember, it's a time function. So it's the amplitude there. All right, that's what we apply to our transformer there. Just quickly want to check something. Yeah, okay. What happens? How does the energy or the power get over to the other side? Well, that current flowing through the coil sets up a flux, but a time varying flux. A time varying flux. D lambda dt is not zero. The lambda dt is not zero because the flux is changing with time. So that changing flux then goes clockwise, counterclockwise, clockwise, counterclockwise, and it changes direction how many times per second? Well, in our country, well, most of the world actually, 50 Hertz, 50 times per second. In the US, 60 times per second. All right, so that goes through that coil, but because the flux then, this flux links coil number 2, and now we remember mutual flux, and this is now where the mutual inductance. This flux links coil number 2, but because the flux is changing through coil 2, Faraday's law induces not a current, voltage. It induces a voltage across those two terminals. You will only get current flowing if you've got something connected between those two terminals. So even without the load, that voltage will still be there. Okay, now if we connect the load, then you've got a current that starts to flow. But now there's a bit of a snag here, you see, because the moment that current that's flowing in this coil, when it flows, it's Lenz's law, it's going to oppose the change in flux. So as the supply side coil, which we call the primary coil, so primary always supply side. As that flux flows through the secondary or the load side coil, so secondary refers to load side. So perhaps just an interlude. Primary and secondary has got nothing to do with high or low voltage side because it depends on whether it's a step up or a step down transformer. Okay, primary is always load side, and secondary is primary is always supply side, and secondary is always the load side. So perhaps if you just quickly go back to this board one, so this one is a step up. So primary will be low voltage, secondary will be high voltage. The step down side, the primary supply side, is going to be high voltage, and the secondary, which is load side, is going to be the low voltage. So it depends. Okay, back to the picture. There we go. Okay, so this current that flows through this coil opposes this flux. I'm trying to push flux clockwise, but the coil wants to push it counterclockwise. And to counteract that effect, to make sure that you still have flux flowing through your core, that forces the source to push current through this. So the voltage potential across the load creates I2, but I1 is created to maintain the flux through the core because I2 is trying to oppose it. I wonder if you can compare it to like Newton's law, one force opposed. Anyway, I don't know. All right. So that's what's happening in that core. Now, the math that you've got on this page just wants to show you, okay, how much if I put in 200 volts there, how much am I going to get out? And it's a relation of the turns ratio, which we did in school. I don't know if you still do it. So here's our V1 of time. Give us the function equals N1 divided dt. All right, Faraday's law. So they calculate the flux from that. That flux flows through coil 2 again using Faraday's law. Now it's N2 divided T. So V2 gives you an expression, and in the end we get that V2 equals N2 over N1. I think not yet, not here. All right. Point being over here is that the voltage ratio equals the turns ratio. Notice the voltage across each coil is proportional to its number of turns. So V2 over V1 equals N2 over N1. All right, so those two go together. So if you know the voltage ratio, you've got the turns ratio. That's open circuit voltage. Perhaps I should just note. Then the dotted polarity thingy, I just want to make sure I'm not skipping something. Dot convention, yeah, that's what I want to talk about next. So you'll notice in this picture there's dots on the transformer here. I wonder, has that been, oh sorry, the hand has been off the whole time when explaining the equations. Okay, but you'll follow. All right, the dot convention, dot on this, dot on the left, dot on the right. So just like we discussed earlier, all it says is that if the AC goes positive on this dot, if you measure on the secondary, it will also go positive on that terminal. Now for a single phase transformer like this, it's just one phase. It really doesn't matter. Your load won't know the difference. It gets AC. But if you were to take 3 of these single phase transformers and hook them up as a 3-phase transformer, and you get the dots wrong, chaos. All right, so my third years have a practical, in the second semester, the third years really look at 3-phase transformers, and they have to take 3 single ones like these, hook them up as a 3-phase transformer, and then if you hook the wrong terminals to on both sides, you need to know where the dots are, otherwise you're going to get terrible voltages. Okay. All right, so that's all that the dot convention there says, and it gives you the ratio again in RMS. I want to then jump. All right, we're going to skip the current, determine the turns ratio. Do I want you to look at that? Yes. So just go, you can go and work through example 15.9. Nothing I can add there. You just read it, you do it. I want to skip current ratio. I want to jump to power. Now we already spoke about the power in an ideal transformer, and we said the power that goes in equals the power that goes out. And I think I'm going to jump to the board on this one. Yes, all right, let me go to the board. Okay, so Sn, let me get rid of this. Sn equals S out. All right, so that means that V1 I1 must equal V2 I2 in our circuit that we looked at. All right, so I1 over I2, bring the I2 over, must equal V2 over V1. What do you notice about the current ratio compared to the voltage ratio? Inverse, equals N2 over N1. And this we discussed when we looked at this figure. Hey? When the voltage goes up, power stays the same. So if voltage goes up on the other side, the current needs to go down on that side. So the current ratio is the inverse of the turns ratio. That's the quick way to get it. And then when they talk about the power section in the textbook, waar is ek nou? Yeah, the current ratio. So this is how I get to the current ratio. And then they discuss the power in an ideal transformer, which is just the fact that power in equals power out. Notice I'm talking S and S because transformers are always rated in VAs, volt amperes. Motors are rated in watts. Transformers are rated in volt amperes. Why? Because they have to supply the load with both active and reactive power. If you've got a poor power factor, then the transformer needs to supply a lot of VARs along with the watts. If you've got a good power factor, then the majority of it will be watts. But either way, all the VAs has to flow through your transformer. It can only handle so much current through those conductors. So if you want more current, you need thicker conductors. Right, so transformers always rated in volt amperes. Right, that covers both the current ratio section and the power in ideal transformers in your textbook. So in one, what's it like, 3 steps, that whole section. Okay, that we've discussed. I want to talk with you through example 1510. Chair, in you come. All right, let's go back over there. They give a summary. Yeah, you can go and read through that summary. It just basically summarizes the voltage ratio, the current ratio, and it talks about power in equals power out, which gives you then the 100% efficiency. I'm not going to look at the mechanical. You can go and look through this if you want. I'm going to talk about this section. I want to get to this example, example 1510. Now, the reason why I want to look at it is it's become it's going to be, it's important, okay? Especially for the next section when we look at real transformers. We're going to look at a concept called voltage regulation, but for that you need to understand what's happening over here. Okay, so we've got a supply 110 volts, 60 hertz, typically standard American, not typically, standard. Goes through a transformer with a turns ratio N1 over N2 equals 5, so you could write 5 over 1. So it's a 5 to 1. So I'm going to somewhat type it in here. It's a 5 to 1 transformer. And that ratio, move block here, I want you to move. There we go. So it's a 5 to 1 transformer. And then consider the source transformer load. Determine the RMS values of the currents and voltages. Currents I1, I2, voltages V1, V2 with a switch open and with a switch closed. With a switch open and with a switch closed. Now let's just talk logic. And I think over here I took a picture, and I'm rather going to talk around. I've got the whole solution in a picture. So just hang on a moment. Okay, so let's work on this one. Where was we? Okay, so let's first look at the scenario where that switch is open on the secondary or the load side. If the switch is open, can you have any currents flowing? No, there's a big hole, so no currents, but the voltage over there will still be 22 volts. How do we get to 22 volts? You take your 110 and you multiply it with your ratio, so you divide it by 5 and you get 22 volts. So it's a step down, eh? It goes from 5 to 1, so 110 divided by 5 gives me 22 volts. So the 22 volts will be there, but because the switch is open, no currents flowing. Now let's close the switch. The 22 volts is still there, but now we can calculate. Let me just get my face out of the way. Ooh, wrong one. Let me just get my face out of the way here. There we go. So now it's 22 volts. Divide by the 10 ohms and you get 2.2 amps flowing on the secondary side. That's with the switch closed. With the switch open, no current flowing. Yeah, okay, perhaps we should say if there's no current flowing on the secondary side, then you can't have any currents flowing on the primary side either. Alright, because if I2 is 0, then through your turns ratio equation, I1 will be 0 as well. With the switch closed, the 22 volts appears across the 10 ohms. You've got 2.2 amps flowing. We use our turns ratio to calculate the current on the primary side. Now the current is going to go up. Okay, it gets multiplied. Go up. Sorry, the current comes down. So if we go from load to supply side, secondary to primary side, the voltage goes up. If voltage goes up, current must come down. Okay, so 22.2 divided by 5, the inverse of the turns ratio, 0.44 amps. Okay. Now I think what's the important bit though, that gives you all the voltages and the currents with the switch open and the switch closed. Alright, now this concept of the switch open and the switch closed and what happens, that's what's going to become important. I want to go back to this one in our textbook. Let me get just my PDF in front of me. So at the bottom of this section, let us consider the sequence of events that I already explained to you. Please go in and read through this paragraph with some care. That's just the whole concept as to why do you actually have current flowing on the primary side when the switch closes. So please go and work through that. Okay, I want to then go on to impedance what do they call it in this textbook? Transformations. In my other textbooks I call it impedance referrals. Alright, let me just get to the right page. Alright, impedance transformation or impedance referrals. What we want to do is we want to take our load on the secondary side and we want to chuck it over to the primary side so that we don't have this turns ratio thing in our way to calculate power in the load. So on the secondary side, the actual load is ZL ohms, whatever value. And then when we bring it over to the primary side, you'll notice there it says Z prime, all right, because we've referred it over to the primary side. Then we basically lose the transformer and you just get a normal circuit diagram. Okay, but what must that be? Now, your textbook is pretty clear on the equations. I'll put another one on the board just now that sums it all up. So we know Ohm's law, V2 over I2 is ZL. We substitute the V2 and the I2 with what we already know in terms of turns ratio, so it becomes V1 and I1. And then we take those ratios over to the other side, and voila, what you see is that that Z prime, or Z1, is now N1 over N2 squared ZL. Alright, on the screen, I've taken a picture that I'm showing you. So there you can see that Z1 over Z2 equals N1 over N2 squared, or Z1 meaning the Z prime and Z2 is your load side. Alright, so in that sense, you can easily calculate the referral to either side. But typically, we want to take it from the load side over to the source side to calculate the information. So ZL prime is the impedance seen by the source. Very little. Or we say that the load impedance is reflected or referred, or what's the word? Or transformed over to the primary side. Okay, so we're going to do an example just now that takes all of this into account. Examples 1511 and example 15, there they've got nice circuit diagram. I would just want to show you the circuit diagram. This is for example 15, 11 and 12. See, there's the original circuit diagram, and then they've taken that 10 plus J20, they've chucked it over to the primary side and they solved the circuit. Then in the B part, they've taken everything on the source side and chucked it over to the secondary side. So you can
just smile and wave, boys. Smile and wave.
Decide which way you want to go, but typically we take the A option or the figure B here, where the load reflected to the primary side. Okay, so nothing I can add, sorry, to those examples in the textbook. You can go and work through them. I want to work with you through exercise 1517, this one. Exercise 1517. Okay, I'm just going to quickly draw that on the board. Exercise 1517, it reads there, consider the circuit shown in figure 1527, which is what I've got up here. Compute the values of I1, I2, V2, and then the power delivered into RL, the 400 ohm resistor, and RL prime, meaning we'll have to shift this over to the primary side. So what they want to have us see there is whether you put the resistor on the secondary or the primary side, the power that goes into the resistor has to stay the same through this ideal transformer. Alright, so we've got 40 ohms for a RA supply resistance, we've got 400 ohm load resistance, and then this VS is a pain in the behind because they give it as 100 angle 0 degrees, but what they don't tell you there is that that 100 is VM, it's the amplitude. Okay, so this is not going to happen in the test and the exams. I'm going to have that little heading that says on the instructions that everything I give you is going to be RMS. So we first have to convert this into RMS. So this equals 100 over square root 2 angle 0 degrees equals 70.71 volts RMS. All right. So it's actually, let's put the angles. I forgot the angle. Well, if it's 0 degrees, it doesn't really matter. Okay, RMS. So since we want to go and calculate power, we need it in RMS. And my answers that I'm going to give you in terms of the currents, the voltages, everything is going to be RMS. So it's not going to be the same as what you see in your textbook, because the textbook has it in amplitude. We're going to do it the electrical way, which is RMS. Okay. First, let's calculate currents, where I just want to double check. So first, let's refer this resistor over to the primary side. So our circuit is now going to look like this. What happens to the transformer? Poof! Gone. All right. The transformer now disappears as this becomes RL prime. This is still going to stay 40 ohms. This is still our VS. So now you've got I1 coming around this corner. So you've got I1 coming around that corner. What's flowing around this corner now? It's still I1, correct? I mean, everything is in series, but from the referred perspective, as I bring this RL across, I've got I2 flowing through RL, so this is going to be I2 prime, which equals I1. Okay, now I can still write a bit with this chalk. Okay, step one, let's get RL prime. So RL prime over RL. Ag, man, para. Ja, is reg. RL equals, okay, now it's NN over NN squared. Which one? Now, I always get confused. So the prime is my number 1 and the original load is a number 2. So N1 over N2. All right, but you've got your textbook, so you're not worried, am I right? So if you refer impedances, and the examples that I told you to go and look at as nice complex, it's got Z's, not just R. So if it's 1, 2, it's 1, 2. All right, so that means that RL prime is going to be RL times, well, let's substitute, hey? Let's somewhere substitute. So the RL is 400 multiplied. What's the ratio? N1 is, oh, it's a 1 to 4. It's a step up. So it's 1 over 4 squared. So we need to divide that by 16, and RL prime becomes 25 ohms. 25 ohms. Right. So here we've got 25 ohms in my circuit. Yeah, if we divide by 16. All right. Now that gives me RL prime. So next, remember, I want all the currents and all the voltages. What voltage is sitting over here? Well, before we referred it was V2. Now we denote this as V2 prime. Okay, now I need new chalk. Now let's go and calculate. What is it? They want all the currents. Now we can go and calculate currents. And this is now in my way. Sorry, I'm just going to get rid of this. 70.71 volts RMS. Okay. There we go. Man, this makes so much dust. But anyway, I1 is now VS over my total resistance. So that's the 70.71 angle 0 degrees. And the total resistance is now 40 plus 25, which is 65. When am I going to get it now? Let's get that then. I get I1 equals 1.09. 1.09 angle 0 degrees amps. Okay. But we know that I2 prime equals I1 equals 1.09 angle 0 degrees amps. So in other words, I2 equals, I want to take it over now to the other side. So I always get confused. I always start with I2 over I1 must then equal N2 over, the other way around, Mugu, N1 over N2. I start there. All right, I'm slow. Which means that my I2, but this is not coming out very nice, is it? So that gives me that I2 must equal I1 times N1 over N2. Yeah. And we know that's 1.09 multiplied with N1 is a 4, so it's 1 over 4, 1 over 4, and we divide it by 4 and we get 0.25, 0.27, what? 2725, 0.2725 angle 0 degrees amps. Okay, I'm keeping the 0 degrees there because they started it, so I'm just keeping it there. The example is nicer, hey, because that I want you to go and look at because it has complex numbers in it. Okay, so that gives me I2. Right, so I2 is sorted. I've got I1 is sorted. What else do they want? They also want V2. All right, now we want this V2. Now, two ways you can get it. I'm just going to get rid of this for the sake of space. So you can either say that V2 equals, you can get it from V2 prime, but now we've already got the caret on this side. So let's just stick with Ohm's law. So it's going to be I2 times RL. So that's a 0.2725 times the, what is it originally, 400, and we get 108.78, 108.78 volts. Everything in RMS. Let's put the angle there just so that everybody's happy. Volts, right? RMS. Just so that you remember. In your spreadsheet, please don't type VRMS. In your spreadsheet, everything is already going to be RMS. Okay. So that gives you the voltage. I see here I made a note on what's the other way to get V2. So you could have said V2 prime equals I1 times, what was it? 25. This one. I1 times 25. So that would give you 27.2 volts. Well, I did a voltage division. Anyway, 27.2 volts. Always a different. Or you could say it's Vs times 25 over 40 plus, well, it was 40, hey? 40 time plus 25 will also give you 27.2 volts. All right? And then you could refer it over to say that V2 then equals V2 prime. Let me just get my V2 prime is like V1, so it's going to be times N2 over N1, I hope. So then it becomes 4 times the 27.2, which will give you the 108. All right, did I write it out all? No. So we'll give you 108.78 volts. Okay, so that's the other way you could have gone about getting V2. Last thing, we've got I2, we've got I1, we've got V2. Now we want to calculate the power in this scenario and the power for that scenario. Next, the last bit, we want to calculate the power for the referred scenario in the load resistor and for the original scenario. Let's do it for the original scenario first. So PRL is I2 squared, it's I2 flowing through there, times RL. Now I2 we calculated as a relatively small current. Where's that one? 0.2725. 0.2725 squared, multiplied then by the 400 ohms, and that gives me 29.7 watts. Okay, so that's if we do it on the original, everything on the secondary side. Now we want to do it with everything referred over to the primary side. So now we need to use I2 prime or I1 through the 25 ohms. So PR, that's a P, L prime is now I2 prime squared multiplied by RL prime. All right, which is just I1 squared times RL. Now, if there was an angle involved, of course, with I1, I see it's going downhill. It's straight from where I'm looking. Remember, this is now active power. So if your resistance over here, if there was another impedance and the current had an angle, when we're talking active power, it's always the magnitude of the current, right? Magnitude. So that's why I'm not bothering writing in the angle there, because I'm only interested in the magnitude. So the magnitude of I2 prime or I1 was 1.0, wasn't it a bit, just 1.09? I'm almost sure I got something else. 1.09. No, that's it. 1.09. 1.09 amps. Squared times the 25 ohms now. Okay, and that will then also give you more or less the 29.7 watts. So it doesn't matter what side you put your resistor or your load on. If you do the correct math, use the correct currents, the power that goes into the load remains unchanged. So what the source sees, I think maybe we should put it like this. For the source, whether I put the load on that side of the transformer or whether I put the load on this side of the transformer, on the source side, it doesn't influence what the load sees, right? And that's what the transformation or the referral needs to accomplish. Okay, that's it for ideal transformers, chapter 15.5. Lecture 27, we will see there's also a little to do there. We're just basically going to work through one example. So that's also going to be a relatively short lecture. We're going to look at real transformers. All right, you'll see me in the next one. Bye.